Power factor basics and introduction. So what exactly is power factor? Well, power factor is a unique measurement that tells us about three different things about our circuit. From left to right, we're going to look at this phasor diagram of the difference between our circuit voltage and the total current. We're going to look at our impedance relationship with our current and our voltage, and we're going to look at our power triangle. So starting with the phasor diagram here on the left, power factor is going to be the cosine of the difference between our voltage angle and our current angle. In this case, power factor tells us how out of phase our current is with our voltage, or how big the angle is that exists between them. Next, looking at our circuit here in the middle, power factor can tell us how inductive our circuit is, how capacitive our circuit is, or how resistive our circuit is. And last, looking at our power triangle here over to the right, we can say that power factor is going to be the cosine of our power angle theta, that's this angle right here. And we can also say that power factor is the ratio of our real power in watts, that's this quantity here, to our apparent power in volt amps, which is the hypotenuse of the triangle. All right, so let's plug in some numbers into our circuit and evaluate this based on a real world example. So we're going to use a voltage magnitude of 120 volts, and we're going to use a total circuit impedance of 5 plus J3 ohms. All right, first step, let's go ahead and solve for the total circuit current, I. So using Ohm's law, we can say complex I equals complex V over complex Z, right? Our total circuit impedance, right? So this impedance symbol right here represents not just the load, but also any line impedance, right? The total circuit impedance. Now, we've got to use a reference angle for our voltage. And to make our math easy, I'm going to go ahead and use a reference angle of 0 degrees. So we have 120 volts at our reference angle of 0 degrees, divided by our total circuit complex impedance, 5 plus J3 ohms. And let's go ahead and plug that into the calculator here on the right. So I've got my fraction sign, 120, then the second complex menu, angle of 0, divided by 5 plus J3. Hit enter. That's going to give us a magnitude of, we're going to round to 1 decimal point, so 20.6 amps. And then I want to look at my degrees. Here's a quick trick. I know there's a lot of repeating decimals here because of that arrow. So all I'm going to do to quickly check the degrees so I know where to round, I'm going to hit up once, highlight it, hit enter on my calculator to bring it back down. And now I can see all of these decimals, and I see that I need to round this 0.9 to 1. So we've got an angle of our current, negative 31 degrees. All right, let's go ahead and use this answer for our current to solve for power factor using this formula here underneath the phasor diagram. So we can say power factor is going to be the cosine of what angle did we use for our voltage, our reference angle when we solve for our current? That's right, we use a reference angle of 0 degrees. So I've got cosine 0 minus, next, what was the angle of our current when we used the 0 degree reference angle for our voltage? We came up with a current angle of negative 31 degrees. So theta V minus theta I. Notice theta I is negative, so I'm going to put one more parentheses here and write negative 31 degrees. And let's see, power factor equals, all right, in our calculator off to the right, I've got cosine, let's clear it first, there we go, cosine of 0 minus negative 31 degrees. All right, that gives us a power factor of 0.857. I'm going to round to 2 decimal places, which is quite common for power factor. So we're going to say a power factor of 0.86. All right, let's verify that answer using our power triangle. So if I want to take the cosine of our power angle, first I need to find complex S, our complex power. So complex power is going to be S equals complex V times the conjugate of our complex current. So that's going to be 120 volts, angle 0, times 20.6 amps at an angle of, normally it would be negative 31 degrees, right? That's the angle of our current, but now we've got the conjugate. So we've got to change the polarity of this angle. We're going to make it positive. All right, in the calculator, 120, we're going to do the second complex menu. We're going to do 0, and then times 20.6 amps. Second complex, pull up our angle. Now we've got that positive 31 degrees. Error data type. Let's go ahead and put a parentheses around this second complex number. Just like that. All right, let's see how that looks. Great. So I've got a total complex power in our circuit of, this looks like what, 2,472 volt amps at an angle of 31 degrees. All right, using this formula up top, let's say power factor equals cosine 31 degrees. So power factor equals, on our calculator, cosine of 31 gives us the same 0.857, or rounded to 2 decimal places, 0.86. All right, let's use this second formula for power factor. So I'm going to go ahead and just make some room here. I'm going to move this out of the way. Okay, now that we've got more room to work with, we also said that power factor is a ratio of our real power P to our apparent power magnitude S. So if we want to get these values, let's first convert our complex power from polar to rectangular. So I'm going to scroll up in my calculator until I find this value. I'm going to show you the easy way to do this. So I'm going to keep going. Oh, I passed it. There it is. I'm going to press enter to bring it down. And I'm going to let the calculator do the heavy lifting for me. I'm just going to hit second complex and scroll down to number 5, which is A plus BI. And when I press enter, it's going to convert this value in polar to rectangular. All right, so now our complex power, complex S, expressed in rectangular is about 2,118.9 watts plus J. And again, I'm going to use that same trick. I'm going to go up, press enter. That's going to bring it back down so I can round easily. So plus J, 1,273.2, and almost out of room, that's VAR for volt amps reactance. So this is our real power in watts, and this is our reactive power in volt amps reactance. All right, let's use this information to solve for power factor using this second formula. So power factor is going to be the ratio of our real power P that we just found for by converting from polar to rectangular. So our real power P in watts is 2,118.9 watts, right? Divided by our total apparent power. And our total apparent power is the magnitude of our complex power. So divided by 2,472 volt amps, it's going to give us a power factor of 2,118.9 divided by 2,472 volt amps. That's going to give us the same 0.857, or if we round it to just 2 decimal places, we have a power factor of 0.86, just like before. Now remember when we said at the beginning that power factor will tell us how inductive with a plus J reactance, capacitive with a minus J reactance, or resistive with no J, our total circuit impedance is? Well, how do we prove that? Well, power factor is also going to be not just the cosine of theta, but it's also the cosine of theta z. And in fact, our total circuit impedance, the angle of that impedance theta z, is actually equal and identical to theta, our power angle. And that's going to look something like this. So we can define power factor as the cosine of theta z, and that's our total circuit impedance. So not just the load, but if we have any line impedance or anything like that, we have to sum it all up, find our total equivalent impedance, and then take the cosine of that angle. All right, how do we find theta z? Well, we know complex z in rectangular form, so let's convert it from rectangular to polar using our calculator. All right, so in my calculator, I have 5 plus J3, and I'm going to go to my second complex menu again. So this time I'm going to scroll down to number 4, which is going to convert the complex number before it to polar. So when I press enter, I've got a magnitude of 5.83 ohms at an angle of 30.9, right? Or we can say the same 31 degrees. All right, power factor is cosine of theta z. That's going to be the cosine of 31 degrees. And just like before, the cosine of 31 degrees is going to give us a power factor of 0.857, or rounded to 2 places, it's the same power factor of 0.86. All right, what happens if we have a resistive impedance? Let's repeat this entire exercise. We're going to use the same magnitude of 5.83 ohms, but we're going to use an angle of 0 degrees for our complex z, and we're going to use the same voltage magnitude of 120 volts. So let's see what that looks like. All right, so here's our same circuit, except this time we've got 5.83 ohms and a new angle of 0 degrees. So I'm going to go ahead and just rewrite this in polar form, because that's typically how you see impedances expressed. And an angle of 0 degrees means z is going to be 5.83 ohms plus J0. All right, just like before, let's solve for our total complex current. Complex I equals complex V over complex Z. We've got the same voltage of 120 volts. We're going to use the same reference angle of 0 degrees. So here's our voltage, 120 volts at 0 degrees. Now our complex impedance we said is going to be just 5.83 ohms. And when we plug that into our calculator, we have 120. And I'm going to show the angle, but anytime you have an angle of 0 degrees, you can just leave it out and the math works out exactly the same. All right, that gives us a complex current of 20.6 amps, just like before, except now we have an angle of 0. All right, let's use this information to solve for the power factor. This is the cosine of theta v. And again, what angle did we use, our reference angle of voltage, when we found an angle of 0 degrees for our current? It was 0. So theta v is 0 minus theta I. Theta I is also 0, so minus 0. So we have our power factor is the cosine of 0 degrees minus 0 degrees is 0 degrees. And that's going to give us a power factor of 1. So notice our current is 20.6 amps at 0 degrees. Our voltage is 120 volts at 0 degrees. Both of them have an angle of 0 degrees, right? Our displacement is 0, right? Theta v minus theta I is 0. That means both our current and our voltage are completely in phase, which gives us a power factor of 1, also known as a power factor of unity. All right, let's calculate our complex power and then use these formulas underneath our power triangle. And you'll notice our power triangle doesn't really look like a triangle anymore, and we're going to explain why. All right, our complex power, complex S, is going to be complex V times complex I conjugate. So I have 120 volts at 0 degrees times 20.6 amps at 0 degrees. And let's go ahead and plug that into our calculator. This time I'm just going to type 120 times 20.6. I'm going to not enter in the angles since they're both 0, and the math comes out fine in your calculator. And you'll notice that I don't get the angle 0 anymore, so that 0 angle is implied. So our complex power is going to be 2,472 volt amps at an angle of 0 degrees. You'll notice that our magnitude is the same, but our angle is different. All right, using these two formulas here, we know our theta, right? Our theta is 0 degrees. So power factor is equal to the cosine of theta, which is 0. And that's going to give us the same power factor of 1, just like before. Next, let's use this ratio. We know our apparent power S right here, but we need to know P. So again, we're going to use our calculator to convert from polar to rectangular. So in my calculator, I'm going to go up until I see my complex power. And you'll notice when I convert from polar to rectangular, it's going to give me the same value. Actually, it's going to say error data type. So let's go ahead and give it an angle. In other words, our calculator doesn't recognize that 0 angle. Let's just go ahead and give it an angle. There's our 0J, right? So complex power is going to be 2,472 watts plus 0J, or plus J0, and that's our reactive power, volt amps reactance. So here's P, this is Q, this is theta, and this is our apparent power. All right, using this second formula for power factor as the ratio of our real power P to our apparent power magnitude S, real power P, looking down here, is 2,472 watts. Our magnitude of complex power, our apparent power, is also 2,472 except volt amps. Look at that, the same number. So when we have the same number on top and on bottom of the fraction, they cancel, right? So we know that this is going to also equal a power factor of 1, or a power factor of unity. Now let's look at our power triangle up top here. Remember, we said it's no longer a triangle, it's actually a straight line. Why is that? Well, first of all, what is theta, our power angle? We found that to be 0. So remember, before our power triangle was up here, but as theta approaches 0, our angle decreases. When theta is 0, our magnitude is going to equal the real component. So our magnitude of our complex power, also known as our apparent power, magnitude S, is 2,472 volt amps. And our real power, P in watts, is 2,472 watts. They're identical. Anytime we have a power factor of unity, it gives us a special condition where magnitude S equals P. Now what about Q? Again, before, when we had a positive angle for theta, we had a value for Q right here. Now, as that angle approaches 0, Q also approaches 0. And once theta is 0, Q is also equal to 0. So now we have no reactive power in our circuit. All right, last but not least, let's look at the power factor as the cosine of theta z. So I'm going to go ahead and just make some room underneath this circuit. There we go. I kept all of the values that we solved for. So if we want to calculate the power factor as cosine theta z, what is theta z? Remember, the only difference between this problem and the last, we kept the magnitude to be 5.83 ohms, but we made the angle 0 degrees. So this is our theta z right here. Again, notice how theta z is 0 degrees. It's going to be identical to what? It's going to be identical to theta, our power angle. So when we calculate the power factor as the cosine of theta z, we get the same cosine of 0, or once again, a power factor of unity. All right, that's it for our first introduction video on power factor basics for our chapter on power factor correction and voltage support. Coming up in the rest of the chapter, we're going to have video demonstrations on the power factor for a three-phase system, both balanced and unbalanced, calculating three-phase power factor from single-phase power factor. We're going to look at the power factor for delta and Y loads, both with and without line impedances. And then we're going to work our way all the way up to doing power factor corrections, where we're going to use capacitors to correct the power factor of induction motors.